Wheatstone bridge. So Wheatstone bridge is the special type of circuit in which we have four resistances are connected as the side of this rhombus, or we can say square if we are like it's better to say square, so we are only rotating this square, or like any kind of this circuit in which we have this four resistance. This can also be like this also, that we will see later. The point is that when you are connecting four resistance together, so you see there are 4 points. Okay, so what we are doing in, suppose A, B, C and D, and suppose this value is R1, R2, R3, R. Right. Similarly, if I represent this as this, so A, suppose I am saying this A, this is B, this is C, this is D. So between A and B is R1, between B and C is R3, between C and D is R4, and between A and D is R2. So you see both the circuits are same, but their way of presentation is different. Now if I make a voltage source, suppose V here, and if I make a galvanometer between here. Similarly, I can do here also. So I can make a voltage source like this, and between B and D I am connecting a galvanometer like this. So what is the purpose of galvanometer? Galvanometer is used to sense the direction, sense the current. Okay, so if there is any current is flowing between this branch B and D, then this galvanometer will sense it and it will deflect. Otherwise, it will be at null position. Null means zero position. Okay, so let us start. I have told you that either I am denoting by this or by this, the same thing. But most of the books use this, and this is easy to understand. But you see, both the circuits are same. It is also a Wheatstone bridge, right? So let us see. If I am saying, so Wheatstone bridge is a bridge in which we choose the value of R1, R2, R3, R4 in such a way that the current flow in this galvanometer is zero. So what we can say? We can say if current in galvanometer is zero, null, this arrangement is called Wheatstone bridge. Okay, this arrangement is called Wheatstone bridge. So what are the advantage if we have sense that yes, if this is deflecting zero value, so this is a Wheatstone bridge, and Wheatstone bridge has a special mathematical relation between these four resistances, and that we will see by this derivation. Suppose I am saying the I current is flowing like this. So what will happen? This I current, I1 will go here, I2 will go here. So the first expression will be I1 is plus I2 will give you total I, right? Now you see, if I am saying the no current in branch BD, sorry, that is galvanometer reads 0. Galvanometer reads 0. So what will happen? This whole current I1 will go here. No current will go in this branch. At the same time, if the no current is flowing in this direction, so this I2 will all go in this branch. So let's see what will happen. Now if I make mathematical calculation. So I can write like this. I'll start from this point, will go that I'm writing here, and if you want to more detail, you can refer my video lecture in which I have given the full detail about Kirchhoff's law and its application. Right. So here I am writing the equations only. So if I write the equation, then I'll get I1 R1 for this loop. Okay. So I1 R1 plus I1 R3 will give you minus V equals to 0. So V equals to I1 R1 plus I1 R3, or we can say, okay, we will do later. Similarly, if I go in this circuit, so what I will get? I will get V equals to I2 R2 plus I2 R4. So that was equation number 2. Okay, and if I write here that we know that I1 R1 plus I1 R3, I am talking about this circuit, minus I2 R4 minus I2 R2 is 0. Now solve this, what you will get? You will get I1 common, R1 plus R3 equals to I2 common, R2 plus R4. Equation number 3. Right. Here you have the value of I1 upon I2. So what is the value of I1 upon I2 here? So I1 upon I2 is given by R2 plus R4, R1 plus R3. Right? Equation number 4. Now also find the value of I here from this 2. So V upon I1 is R1 plus R3. The same we will get. So if I solve this by using the expression, yes, that we know that here I is I1 plus I2. Okay, so I is I1 plus I2, and you put the value of I1 and I2 from here, and then you will solve this. So then you will solve all these 3 equations, and of course by using this equation 4. So when you will solve all equation 1, equation 2, equation 3, suppose this is, I'm not going again, this is the equation 3 and this is the equation 4, where I is given by I1 plus I2. When you will solve all these 4 equations, so on solving, what you will get finally, you will get a very beautiful relation, and this relation is that very simple relation that you will get when you will solve this. I'm writing the expression directly. So you solve this, and when you will solve this, you will get R1 upon R2 is R3 upon R4. Okay. So when you will solve these 4 equations, finally you will try to remove the values of I, the values of I1, the value of I2. Then finally when you will solve, you will get R1 upon R2 is R3 upon R4. So if a circuit, any circuit having 4 resistance in such a way that a battery is connected between A and C, and a galvanometer is connected between B and D, and you are finding there is no deflection in this galvanometer, this implies that your circuit is a Wheatstone bridge. And for this equation, R1 R2 divided by R1 upon R2 divided by R3 upon R4. Okay, so now how can we use it? You know that if you have this expression and if you know the any 4 value, then you can get the 4th value. Okay, suppose I know R3, R4, R2, so I will get the value of R1. So in this way, this procedure is used, Wheatstone bridge is used, can be used to find any unknown resistance Okay, so like how can we use? Simply, I'm connecting an unknown resistance R1 between the branch A and B, and I will adjust this galvanometer to 0. If it is coming 0, this means it is following this expression, and hence I can get the value of this unknown resistance. So this is the advantage of Wheatstone bridge, that we can use it to find any unknown value of resistance or the unknown value of EMF also. Even like if we have a cell, so we can get the value of EMF for the cell, and at the same time we can also get the value of equivalent resistance of the cell. And these methods are the application of this Wheatstone bridge, which is known as the two concepts which are known as meter bridge and potentiometer. So meter bridge and potentiometer are the two applications that are based on the concept of Wheatstone bridge. Okay, so let's see how we can use the meter bridge to calculate any unknown resistance. Okay. So this I am drawing the practical setup of meter bridge. So this is the practical setup of meter bridge, right? Okay, so this is the practical setup of meter bridge, in which we have a table, and in this we have this blue line shows the meter, the copper strips, and this copper strips, between this point and this point a wire is connected, right? Between these two points a wire is connected, and between these two points unknown resistance, this I am saying this R is unknown, we have to find the value of this R, right? And between these two points we connect a known resistance, so this S is known and this R is unknown for us. So now you see what I did. Suppose I am saying a first point, a second point, a third point, a fourth point. Okay, so if I am saying this A, this is B, this is C, this is D, right? So if I am making the same arrangement like previous one, so this is A, this is B, this is C, this is D. So what is between A and B? R, B and C, S, between C and D, Q, and this is P. Galvanometer is connected between B and D, right, and A and C. So you see the whole arrangement shown here as similar that we have discussed in Wheatstone bridge. Okay, now you see this galvanometer is connected with B, and this I am showing my arrow with curved line, it's variable. So in practical what I will do, I'll move this point in this way, from this point to this point, in such a way that this length is variable. Suppose if I am saying, okay, if I am saying the resistance as, like, if this is at point D, right, it is at point D, So what will happen if it is point? If I am saying this is total is you know that if I am saying for this, suppose from this point to this point, total resistance is X. Total resistance is X. Where? Between the point this and this. Suppose I am saying this point is X, this is point double X. So the total resistance between X to double X is small x, right? This length is L. So what will be this length? X minus L. Is it okay? Right? So total resistance of X. So what is the resistance between XD? Between the point X and D, which is I am showing by P. So what is the value of P here? P will be the total resistance X divide the total resistance is X. X is for the total length. Okay, so the resistance of this part will be how much? What I will get? X is the total length. So total length is what? The total length is L. Okay, sorry. The total length is L. The total length I am saying, suppose L. And this is L, so this will be L minus L. Is it fine? So you see, if I am saying what is the value of resistance for the P? So the value of resistance for P is you can get by the unitary method. And what is the unitary method? That is for length L, your resistance is X. So for length 1, your resistance will be X upon L. So for length L, your resistance will be X upon L into L. So this is called unitary method. And the same I am using here. So the resistance of XD, which is given by P, okay, resistance of XD, which is given by P as X times L upon capital L. Similarly, the resistance of D double X means from this point to this point, which I am showing by Q, is given by X. This length is L minus L. L minus L. Right. In meter bridge, in this, we take the length of this wire is 100 meter. Sorry, 100 centimeter, 1 meter length. So meter, because we are calling it meter. So the length between X and double X is 1 meter. So 1 meter means this L, capital L, is given by 100 centimeter. Okay. So if I am touching this point at D, so you see, according to my formula, which I have studied in Wheatstone bridge, what will be the relation? This will be the relation when this galvanometer deflected, no deflection, shows no deflection. The deflection given by this galvanometer is 0. Then this meter bridge is forming a Wheatstone bridge, and for this Wheatstone bridge we have the formula R upon S equals to P upon Q. Now you see, R is unknown to you. S you know the value of S, what resistance you are connected between these 2 points is known to you. Okay, is given by, you see, if I am saying this 100, for example 100, the P, what is the value of P here? The value of P is XL. So X is the total resistance between X and double X into L divided by capital L. So capital L is 100. I have told you that we normally take 100 centimeter. Again X, L 100 minus L divided by 100. So here everything will cancel out. What will remain left? And so R will be S times L upon 100 minus L. So you see, finally what we get, if we are touching our jockey, this is called jockey in technical term. So we are touching the wire which is connected with jockey with this meter wire at point D, and the point D is L distance. At L distance from this end, naturally this distance will be 100 minus L. So this means P will be given by this formula and Q by given by this formula. And since finally X and X is cancelled out, so we can say yes, this is L, this is 100 minus L. So when we will put here in this formula, so finally we get this relation, and this relation shows that yes, we can get the value of R by using the meter bridge concept, and hence meter bridge concept can be used to find the unknown value of the resistance. Right, now let us see the next concept is potentiometer. The potentiometer arrangement is same like this meter bridge. In that, what we do, we simply change, little change we do. In place of using a single 100 wire, we make like this, and these all are connected. Okay, so simply what we are doing, this X and double X, this is called potentiometer. I am talking about potentiometer. Okay, so when we connect like this, so what is happening? If we are increasing the length of the wire, so accuracy will go up. So for increasing the accuracy, we can use in this way, right? And now if I am drawing the circuit of potentiometer, so with this point, okay, so now what I am doing, between these 2 points, I am using a battery. Okay, let me finish this first. So this I am using a battery between the point X and double X, right? And between these 2 points, this point, I am using an another circuit. Okay, that has some kind of circuit, and then it is connected with galvanometer, and this galvanometer can be touched to any point. So you again see what I am doing, the same thing which I am doing here, and yes, of course, I am using one resistance over here. Okay, so again you see we have one resistance here, one resistance here, one resistance between the, suppose this point is O, so between the point X and O we have one resistance that depends on the length like meter bridge, and another resistance like this. Okay, so when you will compare this, the same circuit that you have done in meter bridge will come again. Okay, and this circuit when you will use, you can find, suppose I am saying that one battery is connected here, one battery is connected here. So we can get, by using this potentiometer, the value of EMF and the value of resistance for this battery which is connected through this potentiometer. So I'm not giving you the much detail about it, but if using this potentiometer you can get the value of EMF and internal resistance that is connected between these two, between this connected here. So the whole procedure I am not giving in this video lecture. So the formula finally I am giving that yes, E1 upon E2 is L1 upon L2, and the final formula for R is capital R L1 upon L2 minus 1. So how can we get it? What is the E1 and E2? So E1 is the unknown battery or unknown cell, and this is the known cell, right? This is the known cell. So when you are connecting, in first case you will connect the unknown cell and you will move this galvanometer. Maybe at this point you will get the deflection 0. So this will be your length L1. When now you will connect the known cell here. the known cell value E2 is known to you, and when you will connect, suppose that galvanometer at this point give you the deflection 0. So this whole length will be your L2. So when you will divide it, you will get the value of unknown EMF, unknown cell EMF. In the same way, if you go for the equivalent resistance, then by using this formula, since you know the value of L1 and L2, when you will divide and multiply this R is also known to you. This R can also be known to you. Okay, whatever the value you are given, you know this. So when you will put here, you will get the value of internal resistance. So in this way, we can see that Wheatstone bridge has applications to find the unknown values of resistance, unknown values of EMF, and unknown value of the internal resistance of any cell. And the applications are most popularly used in our laboratory also, and these applications are meter bridge and Wheatstone bridge. So I hope these all points are clear to you. Let me allow to stop this lecture at this point, in which we have discussed the concept of Wheatstone bridge with the application of meter bridge and Wheatstone bridge, and the concept of the cell when we are connecting them in series and parallel. Okay, thank you very much.